Hello, thanks for joining us. This is Space Nuts, and I'm your host, Andrew Dunkley. It's great to be with you once again. And coming up on this episode, we will be looking at liquid on Mars. Is there or isn't there? Yeah, no, don't know, maybe. That seems to be the answer. But there's some new information that we're going to walk our way through, wade through, if you like, on this episode. We'll also be looking at news on organic molecules near black holes. What the? And answering some audience questions about how big a rock would be to pitch Earth off its orbit after what we did with the DART mission. And a solar eclipse next year is going to pass over a solar observatory, which is perfect timing and the perfect placement. So we'll find out what difference that makes to observations. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us as always is Professor Fred Watson. Now, I've just got to do a little bit of work to connect with Fred because Fred's computer's getting a bit old and tired. So just give me half a second and we'll get organised here. Yeah. Just keep working on this. All right, we're nearly there. I'll go and make a cup of coffee while I wait. Close. I think. Yep. Success. Hello, Fred.
Hello, Andrew. Very good to see you today.
Good to see you too.
I need to put another shilling in the meter to get this thing working properly.
I think so. Yeah. I've been playing with the sound effects on my panel and got some new ones.
No,
I love that sound though.
Yeah,
I really do.
It was always back in the day. You knew once those sounds started playing, you knew you were getting somewhere.
Right? Yeah, you wouldn't have a clue these days. They should just fake it.
Yes,
it's lots of fun though. Now we've got plenty to talk about, and the first thing on the agenda is the new evidence. They're calling it new evidence of liquid water beneath the south polar ice cap of Mars. Now, this has been long discussed and debated, and I'm sure there have been some arguments in the halls of science somewhere. What's the latest?
It's a really interesting turn for the probably the positive in terms of what our evidence is all about. So remember, this story goes back, I think, to 2017. I think it was as long ago as that.
Yeah,
when observations made by the Mars Express spacecraft, which is an ESA spacecraft in orbit around Mars, radar observations seem to indicate over Mars's south polar cap that there was a layer underneath the ice that must have liquid water in it because of the kind of radar reflection that was being sent back, returned to the spacecraft. Yeah. A depth of something like, if I remember rightly, I think that ice sheet is about 1.5 kilometres thick. So, down at the bottom of that, there was thought to be this layer of ice. Then there was another paper that came out, which I think has been followed up very recently, actually, with work from the same authors, that said, well, wait a minute, it might not be that because we found radar reflections from places on Earth that don't have ice on Mars that don't have ice on them, and that is probably due to particular kinds of minerals in the underlying rock. I think basaltic rock was one of the culprits, thought to be giving you this bright radar reflection.
I thought I heard something to suggest it might be CO2 ice as well.
Yes, that's right. I think that's actually what the latest results are about. The possibility of CO. No, not the ones we're going to talk about now, because that's the other team. So we should give these teams equal prominence, shouldn't we, on Space Nuts? But we are mentioning them. We're mentioning the opposing views. However, there has been, as you mentioned, new evidence that perhaps the liquid is actually the situation, and that comes not from radar reflections off surfaces deep under the ice, it
Comes
comes
from a
from
Martian tap.
it comes from a Martian app. How did you know that?
A tap,
A tap. Sorry, I thought you
for
said an app.
for our Americans, faucet.
A faucet, yeah.
Mm.
Well, that could be where it comes from, but it's more likely to be ice that's melted because of geothermal activity. That's really the thing that is the clincher with this, if that's the case. But that's the big question. So the evidence now has taken a turn, really from looking at the radar reflections deep down under the ice to looking at the surface topography of the ice sheet itself. In other words, the height above the baseline that this ice sheet is, and it's because the scientists who've been working on this have recognised that on Earth, where there is liquid water underneath an ice flow, and there are several situations where that is the case, it has an effect on the shape of the ice surface itself. And what you've got is this really interesting situation because the water underneath the ice, basically it's sitting on top of the rock bed that supports the ice. So you've got a rock bed, a subglacial lake, and then ice over the top of it. And the ice is moving. This is the situation on Earth, Andrew. And what happens is, because there's water underneath, because of the water in the lake underneath the ice, that reduces the friction between the ice sheet and the rock surface itself. And so it changes the speed of the ice flow above it, and that speed is the ice is moving because of gravity. That's what happens with glaciers. And so what you've got is a situation where, because of that reduction in the friction, it changes the shape of the ice surface above the lake, and what you tend to get is a depression in the ice with a raised area further downstream, if I can put it that way, in the direction that the ice is flowing in. Mm-hmm. And so that's the situation on Earth. And so what these scientists have done is gone off back to their Mars radar data and look to see if they can find something similar above these putative lakes, the lakes that are assumed to exist. And they've found it. This is a group at the University of Cambridge. Actually, it's not the radar measurements that they used to find the surface shape of the ice. They used a laser altimeter measurement. So it's what you might call LiDAR. It's light reflections rather than radio reflections. Yeah. And so that lets them see the exact shape of the ice surface. And they're basically, what they're saying is that they match the computer models for how that body of water that is thought to be underneath the ice would change the surface. And actually, it turns out that this disturbance in the ice surface is exactly over where the radar reflections are bright. And these scientists are saying this really adds to the evidence that there is liquid underneath there that's changing the friction between the ice and the rock surface.
How interesting!
Yeah, it's a very nice piece of work. Whether you believe it or not, it's very nice. Well, it's a nice assumption.
I was reading something the other day about glaciers on Mars and how different they are to Earth because of the different gravity. And they thought for a long, long time that the glaciers on Mars just sat there because they couldn't move because there was nothing underneath. But the new theory is that there is probably water underneath, and because of the low gravity, it doesn't run away as fast as it does on Earth. Okay. And therefore, the glaciers on Mars do move, but much, much more slowly than they do on Earth. So we get the impression that they're not doing anything, but they actually are.
Okay.
If that makes sense.
Well, that does, and that ties in. If you've got this crinkling effect of the surface because of an underlying body of water, that might be quite a long-lived phenomenon. It might be because it all happens so slowly.
Well, they're also suggesting because of the differences in gravity and the differences in the movement of glaciers, the features we see on Mars are very different to more rigid features of Earth. So Yeah, it's really, really interesting. They do tie in nicely. They're totally different studies, I believe, but they do seem to correlate when it comes to the liquid water situation on the red planet. So very exciting indeed. Does that mean a future mission to Mars, should this new science prove to be absolute, would they target those regions as landing points?
Well, you'd expect they might do. That's right. Although you're still going to be a bit hamstrung on how you explore that liquid. If it is 1.5 kilometers down,
Yeah.
you're basically you've got to drill a big hole in the ice, and that always raises the issue of bringing terrestrial microbes to what is currently a pristine body of water, if it exists. So I thought we might. I've just looked up, Andrew, the new paper that's come from the opposing group.
Oh yes.
And we should just give it a mention because it's entitled. It's entitled "Explaining Bright Radar Reflections Below the South Pole of Mars Without Liquid Water." That was published in Nature Astronomy on September the 26th. I've got a feeling that the other paper was published in Nature Astronomy as well. So
I'm just looking at that now, and I think you're right.
Quite interesting. Yeah.
Yeah, it's in Nature Astronomy.
So, and this is a team from the Cornell Center for Astrophysics and Planetary Science in the United States. So they argue that these are reflections, and I think this might be the work, if I just look down a bit further, that you mentioned, which involved simulations. Here it is. The researchers created simulations with layers composed of 4 materials: atmosphere, water ice, carbon dioxide ice, and basalt. And apparently it's the carbon dioxide layers that produce the bright reflections, exactly as you said earlier on in our chat.
There you go. So I'm well read. I just don't remember it very well.
Tell me about it.
Yeah. So I suppose that's going to just create more debate.
Yeah, and it's so people are going to think of more and more ingenious ways that you can actually try and distinguish between the two phenomena. And I think looking for crinkles in the surfaces of the ice is actually a really good one. That's in support of the liquid water theory. So I think this is going to go on for quite some time, Andrew. And yes, in the end, it will be just down to future explorers of Mars, probably robotic, to try and find out what really is happening.
Yeah, because ultimately when humans do go to Mars, they might be looking at finding water, or at least sourcing water that's been found by those robotic surveys to create fuel to get home.
They might
go somewhere else.
Yeah. It's not. It would be highly salty. It would, it'll be very, very high in minerals, probably perchlorates, which is this natural antifreeze that lowers the freezing point of water a long way below zero. Because it's underneath ice. It's at the south pole of Mars. Our south pole's pretty cold, but Mars is 50% further away from the sun again, so it's even colder.
Yeah.
So you've got to look for a way to keep the water liquid if indeed it is there.
So the technicalities once we're on Mars will be significant.
Yes, I think so. Yeah.
All right. Lots of problems to solve, but maybe a step closer to finding out absolutely that there is liquid water on Mars. Maybe.
Or not.
If you disagree, Fred's address is.
Yeah, that's right.
But we'll watch with interest. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let me tell you a little bit about our sponsor, NordVPN. Now, I'm going to do this as I speak. So if I put the URL nordvpn.com/spacenuts into my search engine or into my browser and press enter, it will bring up a special offer for you as a Space Nuts listener. And it's an exclusive cybersecurity package that comes with all the other bells and whistles that NordVPN offers. Now, they've got great credentials. They've been highly recognised by some of the big names in media around the world, including BuzzFeed, Forbes, TEDx, Huffington Post, Wired, BBC. You'll see all that on their website. But what they aim to do first and foremost, and this is what they're famous for, is to protect your online activity. If you're not using VPN, you are leaving yourselves wide open for exploitation, whether that's from a hacker or just from an opportunist, and it can happen anywhere, especially in public Wi-Fi areas. But the deal also gets you so much more at the moment. So if you click on the grab the deal button, which I've just done, and keep in mind there's a 30-day money-back guarantee from NordVPN if you're not happy. Now, they have several plans. They have a 2-year plan, a 1-year plan, or you can go month by month. But I would certainly recommend the 2-year plan because you get so much more bang for your buck. And there are different levels within each of those time frames. You can get the start package, the plus package, or the complete package. So it's up to you which way you go. But the higher you go, the bigger the saving. So 69% saving on the plan that gives you the complete package. So that's your high-speed VPN. Protection from malware. You get a tracker and ad blocker. Cross-platform password manager. They're really handy because so many passwords that you need these days and it's hard to remember them. This will do it for you. Data breach scanner and 1 terabyte of encrypted cloud storage. So check it out. It is a really great package available to you as a Space Nuts listener. Just put in the URL nordvpn.com/spacenuts. That's nordvpn.com/spacenuts. And then click on the grab the deal button and find the formula that works best for you. But NordVPN, the best in the business, and we're very proud to have them as our sponsor on Space Nuts. Oh, don't forget the code word Space Nuts to secure the deal. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, let's move our attention to a very popular topic on Space Nuts and in general, and that is black holes. And the story that we're looking at now comes from Oxford University, I believe, and observations from the James Webb Space Telescope, but it involves organics near black holes. So organics being, I don't know, some kind of plant product that's been turned into pasta?
Yeah, that'll do it. But it's also molecules that contain carbon. That's the definition of an organic molecule.
Yes.
So you're right, Oxford University, and this apparently is the first UK-led research to use spectroscopic data from the Webb Telescope's MIRI instrument, mid-infrared instrument, and it's all about the structure of stuff inside galaxies, and in particular they're looking at active galaxies. And what that means is that you've got a galaxy with a supermassive black hole at its center that is actively consuming the region, the material from the region around it, and causing the black hole itself to become luminous, not because the black hole is shining, but because the accretion disk, this disk of material being sucked in to the black hole, is generating a lot of energy because of the velocities that the material is achieving before it disappears into the black hole, and the fact that energy we see as well radio radiation, infrared radiation, X radiation. So it's what makes a galaxy active. The gobbling up black hole in the middle. So that would be the last place, Andrew, you'd expect, an environment like that would be the last place that you'd expect to find delicate molecules. And molecules are delicate in the sense that if you blast them with ultraviolet radiation, they fall apart. You've got lots of atoms rather than atoms bound together in molecules. So the Webb telescope, being an infrared telescope, was very good at detecting the signatures of molecules with the spectrometer. And that is what has been done with this particular work, which actually centers around data from three luminous active galaxies. What they've done, the scientists doing this, they've looked at what are called PAHs, and PAH or PAH is an acronym for polycyclic aromatic hydrocarbons. And these are the the organic molecules. We know that they exist in the universe. They form in cold molecular clouds, but they might well be a building block of some of the compounds which eventually go into life, what you might call prebiotic compounds. So they may have been very important in the way life kicked off, these molecules. But being molecules, you'd think if you put them near a black hole, they'd fall to bits, and you just have a pile of atoms. But it turns out that you don't. The molecules, despite some earlier theoretical predictions that suggest that these molecules would be destroyed near a black hole in the middle of an active galaxy, these new data have shown that they survive, or they can survive, even where the conditions are at the most acute, where you've got ultraviolet or X-rays that you would expect would just rip them to pieces. And so one of the question is, why are these things surviving?
That's the question, indeed.
Yeah. And the suggestion is that one reason could be that there's a lot of them, that there is you've got these giant molecular clouds which are in the vicinity of the black hole, but not near enough for the molecules, the heavier molecules protecting the PAHs to be ripped apart. So the PAHs are kind of being sheltered by other molecules. There's some more subtleties on this, in terms that some of the PAH molecules might have been destroyed, but the suggestion is that, and the reason is that there are, these things come in different shapes and sizes, and it seems that the larger ones there, the larger molecules actually outnumber the more fragile, smaller ones, and that suggests that yes, those ones, the smaller ones, have been destroyed, or a higher proportion of them have been destroyed by the radiation. So it's all about how things behave in an environment that we can't even get our heads around, where there's high levels of radiation in the vicinity of a black hole. But it is a study that's brought its own surprises. Yeah.
I'm sure. And we get so many questions about black holes, and they are one of the great mysteries of the universe. And I suppose it's going to make people wonder, if molecules are destroyed by a black hole, then what can possibly survive? And
yes.
Now saying, well, molecules can.
Yeah,
so
we are. Yeah, that's right.
Does that suggest something else could survive if the circumstances were right?
Like human bodies made of molecules, for example.
Well, that's a good question, isn't there?
Yeah.
I don't know.
Before you get spaghettified.
And that is, I suppose the time will come where we're able to travel long haul in space if they solve some of the distance and speed requirements. And one of the projects that would come out of that is to get up close and personal with a black hole. And I can't imagine what you would see. And you've only seen them portrayed in science fiction and in images that have been created, and now we've got two images of them that just basically looks like an orange-coated donut.
That's right. Well, what you see is what you get, I think. It's not a donut.
Basically it, but the mystery remains.
It is. Yes. I mean, there are simulations which you and I have both seen, and of course, the Interstellar movie had a fairly good simulation of the vicinity of a black hole. But there are even more accurate ones on the web that show you what it would look like from a reasonably safe region. But we're discovering ever more details about this thing. Who would have thought that molecules could survive in that maelstrom of energy that's coming from the accretion disk of a black hole, let alone the gravity. The gravity itself, that's a different thing. That's what spaghettifies you. But if your molecules have already been pulled apart by the radiation, the spaghettification becomes a secondary problem.
Yeah. Would it hurt?
Yes, it would. Whatever it was, it would hurt, and that's why we don't do it, because it would hurt.
Yeah, well, we don't do it because we can't get there, but
And there's that too. Yes.
if we could ever get there, someone would try and test the logic, I suppose.
Oh dear, yeah.
Yeah. I don't know. I'm not volunteering.
No,
And I'm not going to be one of those volunteers that stands in line and someone taps you on the shoulder and volunteers you. No, not interested. I'll let someone else be the guinea pig. But yeah, and you know, Fred, this is going to prompt more questions from people about black holes. What I love is people come up with theories about black holes and ideas and concepts, and they sort of wrap it all up with dark matter, which is the other big mystery, and dark energy. Those are the big three at the moment in terms of queries from Space Nuts listeners. So,
Indeed.
yeah, look, if you've got any questions based on what we've just heard, by all means, send them in to us because, we'd love to see what you're thinking in terms of that. But it's a quandary. It is. That's what it is, a quandary. Okay. By the way, if you want to read more about that particular study, you can do so in the journal Astronomy and Astrophysics, where it's been published, and you can read that story on phys.org as well. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
3, 2, 1.
Space Nuts.
Okay, Fred, it is question time. And I've got a couple of questions, text questions we're going to tackle today. And we'll start with this particular one. I like this bloke's view. Ramiro from Houston, Texas, writes to us and says, currently sitting across the street from NASA Space Center making a fuel delivery at a petrol station off NASA Road 1. I've probably driven past that, one time. I was listening to the DART episode and came up with a question regarding the change in path of objects. Well, we now know, Ramiro, that it was successful. We heard about that a couple of weeks ago. So his question is, how big does a meteorite or asteroid or comet have to be in order to change Earth's movement through space? Does it speed up or spin faster or slow down? Does it change time? Will it cause the pivot of the axis? And so it goes on. If we could change a rock's course, as we did with Dimorphos, could a really big one change Earth's trajectory, besides the point of climate change and destruction? Thank you both for the show. Keeps me awake on long trips at work. Love hearing the podcast. Thanks, Ramiro. How big would a rock be or need to be to knock Earth off its orbit or shift it slightly or knock it off its axis? And we know probably that this has happened to planets in our solar system at some stage.
That's right. Yes. So it's certainly not a daft question, because we think that's what happened to turn Uranus on its side and possibly even to turn Venus upside down. Although
I might jump in there, because I read a report the other day that said that they're now suggesting that it wasn't one object that knocked Uranus on its back. It might have been multiple objects.
That ties in with some of the conversations we've had recently, though, Andrew.
And they also suggested that it wouldn't have to be anything huge. It could be something the same size as our moon that could have done it.
Yeah. It's usually thought to be something a bit bigger than that, an Earth-sized object. Earth is 81 times the mass of the moon, so it clearly has much more clout.
Yeah.
So that is certainly one of the things that you would expect from a large body. Thinking about the collisions that are assumed to have taken place in the early solar system, that collision between the hypothetical object Theia and the Earth, which generated the moon, that was thought to be a Mars-sized object hitting the Earth, and it almost certainly changed the spin of the Earth, and possibly to some extent the orbit as well, although it's a lot harder to shift the orbit of an object than it is to change the spin and change the tilt or change the rate of spin, because you're trying to deflect the whole object itself rather than just change the way it behaves in terms of rotation. And that's why the DART experiment is so significant, because there's, the evidence is now there that its orbit has been changed by 32 minutes from 11 hours 55 minutes. It's come down to be faster than that, and so that has happened. That's with a half-ton spacecraft. But that was with an object only 170 meters in diameter. When you think of an object 12,500 kilometers in diameter, namely our own planet, and of course, considerably more massive, then to change its orbit needs something really big. And in fact, I think you'd be talking about something whose diameter would be between that of Mars and the Earth. It would be almost like needing another planet in order to bash into our planet, give it a big enough swipe to change the orbit. It's much easier to change the spin rate. And I don't know, we haven't really talked about this, but it seems very likely that the Chicxulub impact that wiped out the dinosaurs, a 15-kilometer object, may have actually changed the spin rate of the Earth, perhaps made a few milliseconds difference to the length of a day, maybe even shifted the pole slightly. We know that the pole does wander around on a scale of a few meters, but something like that could have made a bigger difference. I'm inclined to try and follow that up, because I'm sure research has been done on this. What did the Chicxulub impact do to the Earth's spin, and maybe even its orbit? Because just maybe there might be a very small change in its orbital elements, but that would have to be modelled rather than anything you could measure.
We know there are rogue planets out there, poor old things that have been kicked out of their own
solar systems,
and they're just floating around. Could one of them, rock up one day and give us a nudge?
Well, that's right. In principle, that could happen, given that we've already had visitors from other solar systems in the shape of your favourite interstellar asteroid Oumuamua, and various other cometary things as well. Borisov, that's right, Comet Borisov. Well done, yeah. That the first interstellar comet observed. So, but we'd know about that quite a long way ahead.
Yes. We wouldn't be able to get out of the way, though.
I don't think we'd be able to get out of the way. That's right. If it was on a collision course, I think we'd just try and get off the planet as quickly as we could.
Yes. Yeah, but where would we go?
Well, yes, exactly.
And we wouldn't have time to sit back and wait for the dust to settle, I don't imagine.
No, there might not be much for it to settle onto, really.
We just have to wait for it to all...
Yeah. So the answer to Ramiro's question is it's big. It's got to be big in order to change the orbit.
And have to be a monster, something. What did you say, between the size of Mars and Earth?
Yeah, maybe certainly planetary sized rather than asteroid sized.
Okay. Yeah, it'd be really interesting to follow up on Chicxulub and see if that asteroid did make any changes to our
see what the theory says.
If we got glanced by something that did change our spin rate, that would be hard to live with too. I imagine that would have impact. If it didn't destroy the planet, there'd have to be some impact on life on Earth, wouldn't there?
I mean, the impact itself would, if it was big enough to change the spin of the planet, the impact itself would be.
It couldn't do it through a gravitational effect by passing us close by?
Yes, but you'd be talking about very, very small changes.
Okay.
Yeah, interesting stuff.
Yeah, very. All right. Thanks, Ramiro. Lovely to hear from you. Hope all is well in Houston, Texas. Let's move on to a question from Matt. Hi, Andrew and Professor Watson. Thanks for the great podcast. It's the best podcast in our solar system by far. I think there's one on Neptune that's out there. We'll get there sooner or later. I noticed that next year's hybrid eclipse totality will pass right over the Learmonth Solar Observatory. Does Fred know anyone who works there, and perhaps give us an insight into what extra research can be conducted during the eclipse, given it will occur right over a dedicated solar observatory compared to the portable setups? Thanks for the great podcast. I look forward to it every week. Kind regards, Matt, who is down in Gisborne, Victoria. Thank you, Matt. Okay, so we're going to have a solar eclipse next year that's going to pass over a solar observatory. How fortuitous.
Extraordinary, isn't it? Yeah, quite a coincidence. It doesn't pass over much land, the moon's shadow, and the bit of land, the peninsula in Australian soil that it passes over is going to be very crowded indeed. But yes, Matt is right. The Learmonth Solar Observatory is on the path of totality, or near it. I'm not sure whether it's exactly on it, but it's certainly very close. It's jointly operated by the Australian Bureau of Meteorology, their Space Weather Services, and the US Air Force. So that is, where the collaborations take place to find out more about the sun. And in fact, the stuff they do is quite interesting. They have what are called solar velocity imagers, which tell you what the surface of the sun is doing in terms of its up and down vibrations. They're part of a network called GONG, which is a really appropriate name, GONG. And I do know people who are connected with that network, although not necessarily working at Learmonth. That GONG is an acronym for Global Oscillation Network Group, and it sort of rings like a gong, but it's the sun vibrating, basically, which it does, if I remember rightly, on a scale of something like 5 minutes, it actually oscillates. There's a whole field, Andrew, which we haven't talked about much, even though there are colleagues here in Sydney who are very closely involved with this work. The general field is what's called astroseismology. It's looking at the way stars vibrate, the star quakes. And yes, GONG is doing that for the sun. I might be making this up, but I think there's something called SOM as well, which is the Stellar Oscillation Network Group, and they look at the way stars vibrate. So this astroseismology, about which you can learn a lot. So the GONG instruments will certainly be looking at the sun. They have radio telescopes at Learmonth and a solar radio spectrograph. With it's a fairly low frequency, 25 to 180 megahertz, which is all about looking for solar radio bursts. So you can bet your life all that stuff will be concentrated on the sun during the eclipse. Sadly, I don't know anybody there. So we might not get any inside stories, but I'm sure we will hear the results of experiments that are being done while the eclipse takes place.
What kind of experiments would they be doing, though?
Well, the instruments that they've got are specifically attuned to this idea of looking at the way the sun vibrates. And they're also measuring radio flares from the sun. It's the typical solar observatory work. They don't have a big telescope that produces really detailed images of the sun's surface. We now have one of those on the summit of Haleakala on the island of Maui. It is the Daniel K. Inouye telescope. It is a very, very impressive 4-meter class telescope used to observe the sun, and some of the images that come from it are quite staggering, showing the convection columns on the sun's surface. That's just an aside as to the kind of state of ground-based solar research. Of course, most of the research that's going on with the sun comes from spacecraft. It's these various spacecraft like SOHO, the Solar and Heliospheric Observatory, spacecraft like that are observing the sun.
Yeah. And for those who aren't aware, the total solar eclipse situation it's just a coincidence, and in years ahead it won't be the same because the moon's moving away from us. So the total block of the moon covering the sun will will dissipate in time. So right at this time where the time we're living in now, it's just sheer coincidence that we're seeing this the way we do when we get a total solar eclipse. Is that right, Fred?
It's very spooky, yes. It's a temporary phenomenon, just happens to be taking place when there are intelligent beings on the surface of the planet to watch it and think about it. But I think the estimates that I've said, I did the calculation once, but I didn't take into account changes in the Earth's orbit when I did the calculation. But I think it's something like 200 to 300 million years down the track, we won't get solar total eclipses anymore. They'll all be annular, which means that the moon's disk will not quite cover the disk of the sun.
Yeah. So right now, our proximity from the moon and its proximity from the sun means that they're almost exactly the same size in terms of their disk in our sky.
They do vary because both of the Earth's in an elliptical orbit around the sun, the moon's in an elliptical orbit around the Earth. So their apparent sizes vary slightly. But yes, that the totality is a possibility, and it happens.
Crazy, isn't it? Just, yeah, I love it. And of course, we've got a big one coming up here in 2028.
I think it is, yeah. It goes right over you and right over us.
Yes, absolutely. It starts in the northwest of the state, and it will totally black out the town of Burke, and then it'll move its way down to the southeast across us and black out Dubbo and Sydney. I hope it's a clear day. I'm looking forward to it. Yeah. We'll have to do a live broadcast, although you'll probably be very busy that day.
We'll see how it goes. Space Nuts tend to get a high priority, Andrew. You might be interested to know. Yeah.
Yes. We've worked our way up to number one on Fred's to-do list.
Yeah, my to-do list. That's right.
It's only taken 6 years. Very good. Thank you, Matt. Good question. And yeah, it's quite fascinating. And I honestly didn't know we had a solar observatory in Australia, Fred. How about that?
Yeah, there you go. Well, lots of stuff that you don't know about.
The lack of my knowledge is deep. It's very deep.
Matched only by mine.
Oh, no. You're way ahead of me. Now, if you do have questions for us, don't forget to send them in. You can do that through our website, spacenutspodcast.com or spacenuts.io. And just send us audio questions. You can do that through the AMA tab and the send us your audio question tab, or you can send us text questions via the AMA tab as well. We take both. Don't forget to tell us who you are and where you're from, because we do love to know that. Although sometimes we can pick it up from the accent, just occasionally, especially those Australians. They're always whinging about something. And while you're at the website, check out Astronomy Daily. There are fresh episodes of that almost every day, and I love that the feedback we're getting says that people are using Astronomy Daily to get a little dose of astronomy while they wait for Space Nuts, which is great. I love it. They're working well together. But yeah, Astronomy Daily with Hallie trying to pull the wool over my eyes or give me a bit of a razz. She's always trying something. But yes, that's the place to go. And while you're there, check out the Space Nuts shop where you can get one of those if you're looking on YouTube. That's a tote bag. There's also a mug somewhere up there. Oh, hang on. I've got to move the camera just that way a bit. See, there it is, right there on the corner. And plenty of other bits and bobs, including Fred's latest book and much, much more in the Space Nuts shop online at spacenutspodcast.com. Fred, that brings us to the end of yet another program. Thank you so much.
It is a pleasure, and I look forward to talking to you again very soon.
I do too. Fred Watson, astronomer at large, part of the team here at the Space Nuts podcast, and we thank Hugh in the studio who's made all the tea today. Unfortunately, he can only drink it for himself because we're too far away. From me, Andrew Dunkley, thanks for joining us. Hope to talk to you again next week on another edition of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.